In the previous video, we discussed what happens to a ski jumper as she launches from a ramp. In this video, we will analyze her motion as she flies through the air as a projectile and comes to a landing. The ski jumper in the previous problem lands on the ground at the same level as the bottom of the ramp. And we're asked a number of questions here. How high in the air does she get at the peak of her motion relative to the bottom of the ramp? How long is she in the air? How far horizontally from the edge of the ramp does she land? And how fast is she traveling when she hits the ground? A number of questions that we can ask about this projectile motion, and let's take them one at a time. Now, of course, what we always do is we draw a diagram showing the situation, and this picks up where we left off in the previous problem with the ski jumper leaving the ramp at a speed of 15.1 meters per second at an angle of 15 degrees to the horizontal. Now, the moment that she leaves the ramp, the normal force of the ramp and the friction force of the ramp no longer act on her. And then if we neglect air resistance, that means gravity is the only important force acting on her from that point on. And so she's an object, a projectile, in fact, in free fall. So gravity is the only force acting on her as she flies through the air. And so that means the only acceleration that she will experience is in the y direction, and it is going to be negative 9.8 meters per second. If we call upward positive and forward positive, then this downward acceleration is going to be negative. Remember that her acceleration in the x direction is going to be 0 because there are no forces acting on her in the x direction if we neglect air resistance. And no net force means no acceleration. There is a net force in the y direction from gravity, and so she has an acceleration in the y direction, the acceleration due to gravity. Remember, when dealing with these kind of projectile problems, when it comes time to write out our data, we focus on two sets of data. One set of data for the horizontal motion, one set of data for the vertical motion. We must separate those two kinds of motion. And the first place we separate them is right here at the beginning. She takes off from the ramp at a speed of 15.1 meters per second and an angle of 15 degrees to the horizontal. That means her velocity is going to have a horizontal component, which we're going to call v naught x, and a vertical component, which we're going to call v naught y. Now, as always, x and y make a right angle, and so this right here is a right triangle. And just like we have done in the past with forces, we can take a vector velocity and break it up into its components using the same technique. So we begin with the sine function, sine of 15 degrees. That's opposite over hypotenuse. And opposite the 15-degree angle is the y component of the velocity. And the hypotenuse of the triangle is the velocity itself. And so that gets us a formula for the y component of the velocity, v naught sine of 15. And that turns out to be 3.91 meters per second. We can do likewise with the cosine function. And adjacent to the 15-degree angle, we see v naught x, and the hypotenuse is still v naught, This works the same way as it does with forces. So we get a formula for the x component of the initial velocity, v naught cosine 15, and that turns out to be 14.5 meters per second. So we now know what the initial velocity is in the y direction, and we know what the initial velocity is in the x direction. And so we can start to fill out our data table here. We look at these 5 variables. Time is common to both of them, so we don't have to separate that out. But we do have to separate out all these others. The initial x position, the final f position, the final x position, the initial x velocity, the final x velocity, and the x acceleration, and those similar quantities in the y direction. We must separate them out. So we fill in this table. We will call the initial x position, in other words, right there, that's x naught, and we'll call that 0. And that means our initial y position, however, is up here at the top of the ramp, which is 1.88 meters. So our initial x position is 0. Our initial y position is 1.88 meters. Now we're focusing on the trip up because we want to find this height right here, the maximum height. So if we only care about the trip up, the final y position is going to be that height, h. The initial y velocity, as we've calculated, is going to be 3.91 meters per second. And then the final y position, the final y velocity at the peak of the motion is going to be 0, because the peak of the motion is where she stops going upward and starts going downward for a brief millimicrosecond. Her velocity in the y direction is going to be 0. Not in the x direction, that keeps going. But her velocity in the y direction will be 0. So if we stop caring right there, then that means the final y velocity is going to be 0. And remember, the acceleration in the y direction is going to be negative 9.80 meters per second squared, the negative sign, because we're calling upward positive. Now, we do not know this height h, and we also do not know the time it takes to go up. So, without knowing the time, we can think in terms of the third kinematics equation, except now we write it with the subscript y, because we only focus on those quantities that are in the vertical direction. Right? So this is the kinematics equation for motion in the y direction. And now looking here, we see that h is our variable and we know everything else. So with a final velocity of 0, and initial y velocity, got to be the y velocity, not the total velocity, but only the y velocity, squared, plus 2 times negative 9.80. That negative sign is real important. The final y position is h, and the initial y position is 1.88. Now you have to be very careful about solving this equation algebraically. Just take it slow, take it step by step, and when you do, you get a value for the height of 2.66 meters. So that is her height above the ground. Not above the top of the ramp, but above the ground level, which is what we are looking for. So in this first part, we exploit the fact that the y velocity becomes 0 at the peak of the motion, and that helps us find the position at the peak of the motion. We also have the ability to figure out the time up, how long it takes her to go upward after leaving the ramp. And we can just use the first kinematics equation for that. Notice I've got a bunch of y subscripts here because we don't care about the x motion here. We only care about the y motion. Didn't put a subscript on t because t is a scalar quantity. It doesn't have x and y components. Once again, the final y velocity is 0. The initial y velocity is 3.91. And the acceleration is minus 9.80. And this gives us a time up of 0.399 seconds. 0.399 seconds. So that is the time for her to leave the ramp and reach the maximum height. Now we are asked to find the total time in the air. Well, that total time in the air is going to be equal to the time to go up plus the time to go down. We could figure this out all in one step. But since the initial y position is not 0, this would lead us to have to use the quadratic formula in order to solve the problem. So to avoid having to use the quadratic formula, we can focus on what are the variables on the trip down. Well, on the trip down, the initial y position is the height. On the trip down, the final y position, in other words, right here, is going to be 0. We start here, we finish here. So our starting y position is going to be the height. Our final y position is going to be 0. Our initial y velocity, remember, is going to be 0. And our final y velocity, well, we don't know that yet. The acceleration in the y direction is going to be negative 9.80 meters per second squared. So these are the data for the trip down. And if we want to find the time, well, since we don't know the final velocity, we turn to the second kinematics equation. Once again, we write it for the y direction using only y quantities. This equation simplifies quickly because v naught y is 0, so this part here drops out. This is also 0. And so we get 0 equals the height, 2.66, plus 1/2 times minus 9.8 t down squared. Solving this equation for the time down, we get a time down of 0.737 seconds. So it takes 0.399 seconds to go up and 0.737 seconds to go down. And so the total time in the air is the sum of these two, 1.14 seconds. And in the next video, we shall answer the other two questions.